All right, that's number 5. Number 6 is asking us rank the following elements by electron affinity from the most positive to the most negative EA value. So this is number 6, right? Yeah. Number 6 says I care about rank by electron affinity, and from most positive to most negative value here. So when we talk about positive, this is my shorthand for positive, and this is my shorthand for negative. Positive means that energy is being absorbed, right? So energy is absorbed. You can think of it as a endothermic reaction. Negative values is energy is released, obviously. Is released, and you can think of this as an exothermic reaction here. And I want to rank these guys here. So I have Br, bromine here, which is in blue actually. Did it freeze on me? No, there we go. So I have bromine here. I have sodium, so Na. Tellurium is Te, I believe. Te is this guy here. Helium is He, and finally phosphorus is P, right? So let's look at this topic of electron affinity first. What is electron affinity? So what does EA stand for? Well, electron affinity here, as the solution says here, is the amount of energy released when an electron is added to a neutral atom, right? So I'm basically measuring the amount of energy when an electron is being added to the atom here. So I can say here, measure of energy when electron is added to element here. So let's talk about bromine first. So bromine here is our halogen group here. Very, very, very electronegative first, so it actually likes electrons. So if I add an electron into my bromine group, it's going to like it, right? I'm gonna Br has 7 valence electrons here. If I add a bromine here, it's going to be great because I want it to. It's going to release a lot of energies here. So bromine here will probably be the most negative here, and bromine here, as you can see here, bromine here likes this likes the electron that's being accepted. So again, I'm going to have a positive. It's going to energy will be absorbed. Right? Energy will be absorbed here. Same with sodium. So sodium here, however, sodium again, if I add an electron to sodium here, it doesn't really make a difference. Sodium doesn't really make a difference because I have 1 valence electron. If I add another one here, it doesn't really release a lot of energy, just because again, it's still it's going to have a charge of 2+. It doesn't really do anything here. So let me just write down I can write down some of the sample equations for you. So I'm going to basically write Br here plus 1 electron is going to give me Br minus. Same with Na here, plus 1 electron is going to give me Na. Na. If I add an electron here, it's going to I'm going to get Na minus. Yes, Na minus, and then so on and so forth here. So again, so sodium again doesn't really react much here with the electron that's being placed here. Tellurium, for example, here, because it's so far down in terms of the periodic table here, if I put a electron into to tellurium here, it will energy will be absorbed here, right? So again, I know that because if I'm looking at the column here, electron affinity increases in periods from left to right and decreases from top to bottom. So it's going to decrease as it goes from top to bottom here. So tellurium is pretty down in the it exists pretty Yeah, it's not that, it's pretty far from the top of the periodic table. So this here would mean that I don't have a lot of electron affinity here. Same with bromine as well here. So again, the energy that's being released is not that much. So tellurium and bromine are correct here in terms of the order here, because they're very much like electrons here. But once they like electrons here, their only energy will be absorbed here. It doesn't really matter if I add an electron, because I don't get a lot of energy that's being released here. So tellurium and bromine are correct. Sodium is next here because if sodium doesn't want an electron. It wants the electron to be taken away, right? So if I add an electron to sodium here, it's going to release some type of energy. Same with this phosphorus here. Phosphorus here exists pretty high up on the periodic table here, and again, this has 5 valence electrons. If I add another one here, it's going to release some type of energy, right? And if I want phosphorus to become a neutral atom here, I would need 3 more electrons. And this is only giving it 1, so therefore it will release some type of energy as so. And then finally, helium is going to have the most negative electron affinity here because it's helium has 2 valence electrons. It's already happy, right? If I make a anion that is helium or helium anion, is going to release a lot of energy here because helium doesn't want another electron here. It's already stable as itself. So even if I decrease the amount of electrons or increase the amount of electrons here, it's going to make it very, very, very reactive here. So this solution here is correct. Good analysis here.